Hello, delegates. Hello to those joining us virtually. It's a pleasure to be with you. I really appreciate your time and the opportunity to speak with you about things that are big, hungry, and messy. This is not a description of me on Taco Tuesday, although that would apply as well. What we're talking about here is the data in an AI pipeline and the infrastructure required to create value from that data. I want to start with a picture. Look at this for just a second. Can anyone tell me what's wrong with this image? It does look like a Bart Simpson.
Three fingers.
Then
Yes, Bart Simpson has 3 fingers.
That's right. Yeah. So one hand is anatomically correct number of fingers for most of us. The other one is missing one, giving us a total of 9. This is the prompt that I used. It won't shock you to find out that was an AI-generated image that we just looked at. I asked the Bing image creator, which is powered by DALL-E, last week with this prompt: give me a picture of a person's hands with fingers interlaced. It took me exactly 1 try to get one with the fingers all messed up. It was not hard to create that image to bring in here and show to you. Why is that? Well, for one thing, the model that I was asking to generate an image doesn't have any intrinsic understanding of what a hand is. It doesn't know about a skeletal structure or how the sinews connect or how a person uses a hand. What it does is it predicts my desired output. When I give it a prompt, it predicts what I want to see most using the parameters of the model, the weights and biases that are generated as part of the training process, right? Those parameters are based on the training data, the set that was shown to the model at the start of the development process. And that training data is composed entirely of images that tell the model what a hand appears to be, but tells the model nothing about what a hand actually is, does, how it's used, right? What's so hard about hands in particular relative to create an image of a car for me, or a face, or a Ferris wheel? I mean, nobody here seemed really surprised that the model got the hand thing wrong particularly, right? Why is that? It turns out there's a few specific reasons for that. One is that human hands are capable of an extreme variety of positions and movements. So interacting with objects, waving, clasping, front of the hand, back of the hand. There's many, many permutations of how a human hand shows up. Also, when it comes to human anatomy, we as the audience have we accept a low margin of error in how we perceive those things, right? So there's something that just feels weird when we see that. We may not know exactly, what it should look like under the hood of a car. If I pop open a car, I ask AI to generate that image. Many of us who are not gearheads in the room may not be able to look at that and say the number of pistons is wrong or whatever the case might be. But we've all got hands and we all know generally what most hands should look like. And so we're very sensitive to errors in how that output is generated. And then finally, there's challenges around how that whole process starts, right? We mentioned the training data set being where this all kicks off. So there's challenges around how many images of hands are available for Gen AI models to train on. Of those images, how many are showing hands prevalently, right? There's a lot of images of people, there's a lot of images of social scenes, but how many of those really contain a lot of information about hands particularly in them? There's a lot of overlap or interaction between hands and other objects in images in a training data set, right? Which creates challenges for the model as well. So these are some of the reasons why hands continue to be one of the sort of giveaways that a model's been generated, or excuse me, an image has been generated by an AI model, right? Text and signs and stuff like that are another one. A lot of models haven't quite nailed that. So you'll see something that looks like half of a word and then some sort of, weird cryptic symbols blended in. There's other things too, but what I'll argue and where I'm going with this in the context of this presentation is that the challenges that exist for hands here are not specific only to hands, but they exist to different extents for a lot of different AI use cases. A lot of different AI use cases are dealing with extreme variety of permutations in the data you're either inputting into the model or seeking as an output. A lot of times there's a low margin of error. You can think about a lot of safety critical or business critical applications where we just can't accept, models fouling simple things up like how many fingers are on a hand or how many, in our financial or marketing plans, transposing figures could be catastrophic, right? And then limited training data continues to be a challenge for a lot of these use cases as well, whether we're talking about healthcare, automotive, oil and gas, really any field you'd want to apply an AI model in, you need quality data at the beginning of that process in order to have a model that creates anything of value as an output. So I'm going to attempt to summarize that here in the upshot. This is my one sentence capturing where we're going to go. Training data, quality and quantity is essential. The AI model output value, therefore use lots and make it good. If the format of that sentence feels familiar to you, you may eat a lot at Chick-fil-A like I do. This is a famous quote from their founder who said, "Food is essential to life, therefore make it good." But the principle applies in AI as well. Okay, by way of a quick introduction, my name is Ace. I'm very glad to be here with you. This is my second field day experience. We were here in April for the first go round and had a very positive experience there. Really appreciated the feedback from the team and the opportunity to share a little about Solidigm. Joining me today is Mansoor Rahman, and he'll be talking to you a little bit later about some specifics around data center TCO optimization and energy efficiency. So you'll hear from Mansoor a bit later. Okay, this is where we're going to go. This is our roadmap for the day. We'll do a very brief AI industry landscape. We'll talk about the AI data pipeline. What is that? What do we mean when we talk about that? What are the component stages of that? And what do we need to know about them from a data infrastructure perspective to make good decisions, to optimize for performance, for energy efficiency, for cost, for rack space, whatever our goals might be. We'll talk particularly about the opportunities and challenges at the edge. That's a huge trend, I'm sure you're all aware. There's a great movement with both hardware and software innovations in recent years to bring as much of that compute as close to the data as possible, right? But it also creates challenges in terms of constraints at the edge. So we'll talk a little bit about that. Then we'll run you through some TCO modeling, looking at different data infrastructure scenarios. We'll talk about the energy crunch and how that's not some scary 2030 forecast that's floating around out there, although we do see those, but it's a problem today, and we're hearing that from some of our leaders in the AI space. And then finally, we'll wrap it up, and we'll talk to you a little bit about Solidigm's product portfolio and how we apply some of our SSDs to solve these problems for customers in the real world. Okay, so briefly, I want to start with what I consider to be the intro slide to every AI presentation I've seen in the last, call it 18 months. It looks like this. Does that look familiar? Has anyone seen a slide like that to kick off? We'll talk about what that could be. So the presentation usually starts with some phrase like "in the AI era," and then it shows this, right? And depending on and delegates having, I think we're your fifth session, you've probably seen it. I was just at the AI Hardware Summit a couple weeks ago. I sat in on about 30 sessions, and probably 29 of them started with this. Right? And depending on who you're hearing from and what their goals are, we might be talking about the amount of investment going into the AI space. We might be talking about adoption or the proliferation of many different use cases and models. We might be talking about how the parameter count on some of these foundation models is skyrocketing into the trillions. We might be talking about how much compute capacity is needed to train those models, right? All that stuff is true. All that stuff, I'm going to assume we'll all just accept as given, that this stuff is growing, it's growing fast. We don't need to review the data and really provide the landscape in that way. I do want to focus our conversation on two charts that are also up and to the right. Okay, so we do have some. But the two that we're going to focus on here for this conversation, one has to do with the magnitude of data that's required to train these increasingly sophisticated and capable models. And one has to do with the energy consumption associated with both training and inference of those models, right? So the chart on the left is from MIT. It's new data. This is showing the median size of training data sets over time. And you can see it's an exponential growth. Those of you who have been following AI for a while or familiar with the history will know in 2017, the landmark paper from Google was published, right? All you need is attention, introducing the idea that eventually led to ChatGPT and everything else that has followed. And that is also the moment in time when we start to see this curve happen, right, in terms of training data magnitude. On the right, this is information from McKinsey. And what this talks about is energy consumption. This particular view is focused on US data center energy consumption. But as I'm sure you're all aware, the same trend is happening globally. You could look at how this is playing out in Europe, where it's even, they may be already sort of hitting that scalability ceiling, and a more stringent regulatory requirement sort of environment is evolving there relative to the US, but we're all headed in the same direction. What this chart tells you is a couple of things, which I really like. The numbers on the curve itself talk about energy consumption in absolute terms, in terms of terawatt hours from 23 to 30. And you can see it's, we're going from 155 to 400. So we're growing quite rapidly. The blue circles on the bottom talk about what is that energy consumption as a proportion of all energy consumption in the United States. And that is also growing at an alarming rate. And we're getting to where by 2030, almost 1 in 10 terawatt hours consumed in the United States is going into a data center. Start to see all sorts of interesting stuff happen as a consequence of that. You start to see software companies building nuclear power plants or reactivating 3 Mile Island, and these things in the news that are kind of wild, right? There's a lot of work to be done. I don't think anybody disagrees with the potential we're seeing, but all that has an energy cost. And so we're going to talk about the storage contribution to that and how optimizing the data infrastructure within your AI cluster can mitigate some of those challenges and buy you either a lower overall power budget or allow you to scale more compute within the same budget, if that's your goal. This is a very new data point. I just added this one yesterday because I liked it a lot, but this is from Digital Realty. And they did a global survey, and they asked a whole bunch of enterprises, what's the main challenge to your enterprise when it comes to adopting a formal AI strategy? The number one response in that survey was lack of data storage required to house the massive data sets that AI needs. Number two was compute. That was surprising to me. It may be surprising to you too. I mean, we're all breathlessly awaiting the arrival of the Blackwell chips, right? And I think Jensen Huang was just quoted this morning as saying demand for those is quote unquote insane. Everybody wants to be first and everybody wants to have the most. And of course, that's in the headlines daily. How much compute is needed for these workloads and how eager hyperscalers and everyone else are to get their hands on compute. But what we're hearing from enterprises is that's the second biggest thing that keeps me up at night. The main one is the data storage, because these data sets that we're training the models on are getting bigger and bigger and bigger. And it's difficult to find enough storage or to do so in a way that's feasible, that's optimized, for the constraints that enterprise is facing when they're building out their infrastructure. Okay, so we've set the scene a little bit. Let's talk about the AI data pipeline, and let's do that by following a bit of data as it moves through the pipeline. If you joined us in April, you saw an earlier version of this. I'm assuming it's new to many folks, so I'm going to talk through it briefly, address each stage along the way, and then there's some information in the table on the bottom that I want to make sure we discuss as well. But when we talk about an AI workflow, really end-to-end, Solidym's perspective, and I think you'll find this aligns with most others in the industry who are sharing their versions of the pipeline, it breaks down into 5 steps. So you start with ingesting a whole bunch of raw data up front, right? If you're building a large language model, that might be the common crawl corpus, millions and millions of web pages and a whole bunch of text. It may be if you're, deploying some AI kind of error detection solution on a factory floor, it may be a bunch of sensor data from cameras in your environment. Whatever the case is, you got a whole bunch of data that you need to put into the funnel in order to help your model understand what it is you're looking for. But that's not usable in raw form, right? So step 2 is data prep or pre-processing. That's where we're doing things. We're cleaning up the data. We're filtering out useless stuff. We are deduplicating, we're normalizing, we're vectorizing into these nice rows and columns in a way that makes it usable to the model as what we call tokens, training tokens for the model. And so that is a discrete step apart from just ingesting the raw data. The prep stage happens to be today predominantly sort of CPU intensive work, but a whole bunch of data is moving through the funnel in those first steps. It's getting smaller as we go. The magnitude, you see the first row of the column there kind of talks about data magnitude. And this is really, we're painting things in broad strokes here, right? The answer with everything in AI is it depends. But if you use the example of a large language model, you may start with petabytes of data in your raw data set. Through the data prep process, you may end up with 10% of that as your training data set that's been cleaned up. And then you move into model development, which has a bunch of sub-stages. There's, of course, training, and that's where you're exposing your nascent model to the training data set. You're showing it those tokens in random order, and that's by design. Depending on the size of your model and your infrastructure, that can take a really long time. And so that's where checkpointing and restore comes in. This is a step that, particularly if you have a training epoch that runs into the weeks or months, which is not unrealistic in some cases, becomes increasingly important, right? You don't want to lose all your progress because you have a hardware failure or a software issue along the way. And so some developers are checkpointing every 10 minutes, some are checkpointing every 30 seconds. There's some discretion there. But the bottom line is to write the checkpoint, which is, sort of your in-flight state of your model to disk, is a sequential write activity, and it requires high-performance storage. Because if you're taking too long to do your checkpointing, your GPUs are not busy. They're waiting while those checkpoints are being written, and it can cost you a lot of time and money if you're not optimized for fast checkpointing. Restore is, of course, the inverse of that. If something does go wrong, and it's mostly a sequential read from disk where you're bringing your model back online from its last saved state. Then at the end of model development, there's a couple of steps, and there's different flavors of these. We won't go into them in great detail, but validating the model is typically done on either a separate data set from your training data set or a subsection of it that you've sort of cordoned off that the model hasn't seen yet, and you're showing it now, and you want to make sure that the outputs are as expected. And then quantization has to do with reducing the precision of the parameters in the model. There's a couple reasons you do that. One is it reduces the overall size of the model, makes it more compact. It also makes inference occur more quickly on a highly quantized model. We have it at the end of model development. It can also happen during training. There's an approach called QAT, I think, quantization-aware training, where these things happen at the same time. But in any event, ideally at the end of this, you come out with a model that behaves as expected. It's sort of efficient and well quantized, and you're ready to deploy. Then you move into the light blue boxes, inference, and more these days with generative models, you have a RAG component, retrieval augmented generation, where you're connecting that model to external sources of data that it was not trained on, right? This may be your corporate SharePoint, your email inbox. If it's like an enterprise environment, you're doing an internal RAG setup. It may be, Wikipedia or news sites, or, for broader kind of.
Every time somebody talks about RAG, you need to put a Michigan J frog icon up there.
I'll remember that. Thank you. And inference, by the way, and when we're talking about energy costs, which we'll get into later, training is the thing that happens once, right? Or maybe a couple times if you have a couple of epochs, but generally it's not something that's done over and over, whereas training very much is. And so that's where I think a lot of people overlook the energy costs. We're all aware that like having thousands of GPUs churning in a data center to train a model sounds really hot and expensive and consuming tons of energy. But once that's done and the model's ready, each time inference is run, each time there's an input and an output, has a relatively smaller cost, but it may occur millions of times, right? And so in aggregate, the energy costs there really add up quite substantially. Finally, the last step is archive. So you're taking that data, both the inputs and the outputs, as well as the enhanced context that you might have grabbed from a RAG source. That all needs to be stored somewhere. There are reasons why that's a good idea from just a model quality standpoint. You may want to use it to train or fine tune later. There are increasingly, as time goes on, regulatory and compliance reasons why you must retain that data. And so having high capacity at the end becomes important again as well. So that's kind of the flow and how a bit moves through. My internet connection's unstable. Hopefully that doesn't slow us down. Let me know if you guys see any issues on the stream. But if we have a single bit moving through, that's sort of, how many of its friends do we expect to ride along the way on the top line there? That's your data magnitude. The second line is the predominant IO type associated with each stage. It's not 100%, of course. Nothing is 100%, but generally, for example, training, we see more random read operations on the storage subsystem than anything else. And checkpointing, more sequential write, and so forth. So these are the performance vectors that we tend to think about as most important associated with each phase. And then on the bottom is kind of where the work is occurring today. There are, of course, examples where end-to-end this is all done in a core data center, but more and more the work is being distributed, right? It's being distributed to regional data centers, which we call the near edge. It's being distributed to edge servers and endpoints and stuff like that. We'll give a few examples later. That's what we call the far edge, right? And so the work can occur increasingly in a variety of different places that we have to think about when we think about optimizing our data infrastructure.
My discussions is around the indexing and the vector databases. And that when they are indexed, the data, we're talking I've heard the numbers of 3 to 10 times explosion of that data. Mm-hmm. And that depending upon where you are with that process, that has to be kept because of the compliance pieces or whatever.
Right.
Have you guys started looking at that and that impact? Because that indexing is happening if we're, the RAG situation. And also if we get to what we had discussion in a couple prior ones is real-time feeding of the data into RAG.
It is something we are certainly aware of. It is something we're hearing from customers.
Okay.
We're running a project internally now to capture a bunch of, firsthand data on that. And invite us back next year. We'll give you a full report out. But certainly
that's decades from now.
Okay. So we've talked about how data. Yeah. Sorry. Go ahead.
Question on the previous slides. I really liked the way you have structured AI pipeline and tagged it with the IO workload types. It is very interesting. Regarding data preparation, a lot of sequential read is there, but do you feel that once that data is being prepared and then written back, a lot of random writes will also be there?
That's right. Yeah. So we have more detailed versions of this that I didn't bring today that kind of talk about those ratios. But yeah, for example, data prep in the workloads we've studied or we've looked at, jointly with our customers, we're seeing like 90-10 read write, and it tends to be sequential reads up front and random reads as you actually, spit out your training data set.
Okay.
Exactly. Okay, so that's kind of step one of understanding how data moves through the AI pipeline. Step two really has to do with where physically does the data live in an AI cluster. And later on, we'll do some magic and we'll combine steps 1 and 2. And that's kind of how we get to Solidym's product advocacy about what products are most suitable or best optimized for customer goals relative to AI deployments. But it's important to know up front that generally speaking, again, it always depends, but generally speaking, within a data center environment, AI data lives in one of 3 places. It either lives in the GPU servers. You imagine an NVIDIA DGX H100. There's 8 slots in there for U.2 drives, right? And I think they're filled most often now by like 4 terabyte drives. So that's, 30 odd terabytes of data in a GPU server. That's one place. And that tends to be highest performance. It's closest to the compute. If you could put everything there, you would. Of course, you can't. That's why there are so many memory technologies and tiering approaches. The second place, moving to the far right, is the object storage tier. So that's really when we talk about ingesting or archiving petabytes of data, we're not doing that in the GPU server, right? We're doing that in these really big storage servers, JBODs, that exist in racks next to all the compute components, right? And that may be petabytes or tens of petabytes of data, depending on, the developer and the use case. But much lower performance relatively, right? And today, that's 90% of that is done on hard drives still for reasons of economy, for reasons of lower CapEx. It's a lot cheaper to buy capacity in a hard drive than an SSD up front. Manzoor will help us understand the longer term picture and the TC argument about how that plays out over a 5-year period. But that's the other place where you see a lot of data. And then in the middle, in these deployments where you have most of your data on hard drives, it becomes necessary to have a middle tier, right? Tends to be all flash, tends to be TLC NAND. And that just exists to ameliorate some of the issues of having so much data on your slow storage. It helps cache it and move it to the GPUs more quickly as needed, right? So we're going to take the slide we just looked at, step 1, the data pipeline. We're going to combine it with this one. We're going to do a little hand waving, and we're going to end up with a very busy slide that I'm going to talk you through here in about 5 minutes, okay? So when we understand that AI work is composed of discrete stages that have discrete I/O requirements, and when we understand that the data lives in specific places within an AI cluster, we can start to map out, okay, how does the data actually move around as we do the work? And so the 6 images you see here, that's the same cluster 6 times. The key up top kind of indicates we're talking about, with the blue overlays, we're talking about read activity. With the red ones, we're talking about write. But as an example, to help get you oriented, step 1, data ingest, tends to be a large sequential write to your object storage, right? So you're grabbing that common crawl collection of web pages, or wherever the case might be, you're dumping it all on your bulk storage because it's the cheapest place to put it to start, right? But you can't work on it there. It's just too slow. It's not feasible. So what you've got to do is you've got to move that data in step 2 from your object storage to your GPU server. So you're reading from object storage, you're writing to your DGX servers, right? And then we're doing what we just talked about, which is a bunch of reads up front and some writes at the end to output your training data set. So that's what's occurring in step 2. Step 3, all your data is, your training data is on your GPUs, on your GPU servers in that those direct attach slots adjacent to the GPUs themselves. And it's a whole bunch of random reads. And you're flying through those tokens. You're showing them to the model in random order by design, because you want to avoid, sort of overweighting or biasing any particular thing that the model might see. So you want to show them in random order. And as part of that, the model is doing a lot of random reads from disk, and it's writing the output of that, which is the completed model at the end of that stage in the process. Same time, sorry, go ahead.
So what are the data sizes? There would not be one particular size, but range of data sizes for each of these steps.
The answer is always it depends, right?
Yeah.
But generally, I would point you back here to where we've seen from ingest to prep.
Okay.
We've seen, 100 petabytes or 100 terabytes, whatever the case be, go to a tenth of that. For the model size, we've seen it again get reduced to like a tenth of that. There is not a lot of the foundation model developers share this information very readily.
Okay.
But there is public information about GPT-3, which is a little older by now, right? And I'm going to do my best to recall from memory, but don't quote me on this. It's out there on the internet.
Right.
It was something like a 800 terabyte raw data set that went into a 45 terabyte training data set. that turned into like a 500 gigabyte model. And so that gives you a sense in that example of how the data is getting smaller before it gets bigger as it's deployed.
Right.
And that's why I was brought up the point about the vector database situation, because I'm thinking that that middle piece there starts to change because, or somewhere, I guess maybe that's the RAG piece of it where it's changing is the terabyte piece of it. Okay, never mind. I think I answered my own question.
Right on. That's my favorite kind of question. Okay, good question over here as well. So the data is, we're dealing with smaller magnitudes as we approach the middle, and then we're blowing it up again at the end. I'm calling checkpoint 3A. It's kind of shown here in sequence after training. That's just so that we can talk about them separately. But as we discussed earlier, checkpointing is happening during the training process, right? And that tends to be large sequential writes, just committing your current state of the model to disk. You're doing that as often as you feel you need to sleep well at night. And then in the morning, when you wake up and you find out that things have fallen apart, if you happen to need to restore, then that's a sequential read from disk, right? Inference occurs, and again, this example is all within a data center. We'll break it out and we'll look at the edge separately next. But within a data center, inference is occurring, and you're getting hit with a lot of random read requests as inputs are coming into the model as it's running through the model. If you're dealing with a generative model where the outputs are much larger than text, you're talking about images or videos, then obviously the proportion of write activity is going to get bigger and bigger. And more of that would turn red, depending on what kind of model you're dealing with. And then finally, at the archive stage at the end, we're moving all that stuff off of the GPU servers, and we're saving it back in object storage where it's cheap, and we can hang on to it for as long as we need, right? Either to kick off another round of training in the future to make our model even better, or to have the right answers when the regulators come calling. So this is, like I said, sort of A plus B, the data pipeline plus the data tiering. We'll revisit this toward the end of the presentation when we talk about what does Solidigm actually recommend and why. It really comes back to this understanding of where the data is and how it moves around in the course of doing work.
So in these many steps, there are a lot of places where we have sequential writes requirement, like ingestion, checkpointing, and archive. But their bandwidth requirement could be different, right?
Yes.
Even for the same type of IO characteristics.
Absolutely. Absolutely. It's highly dependent on the use case, right? If you're ingesting in a big batch up front, like the common crawl example, you may care a lot more about your write bandwidth because you don't want to wait around forever for that to happen. If you're kind of streaming stuff in from sensors or whatever the case might be, your bandwidth requirements could be very different.
And bandwidth requirement for checkpoints would be very high compared to ingestion and archiving, right?
It depends. There's a formula actually, and if you want to follow up after, we can chat about that. But how big is your model? How often are you checkpointing? You can sort of compute like what's your ideal required write bandwidth to do checkpointing in a way that doesn't interfere with your GPUs too much.
Got it.
Yeah. Okay, let's look at the edge for a bit. And I want to start by talking about how AI models get built and deployed, apart from the technical steps we just looked about, who's doing it and where are they doing it. So obviously you have the hyperscalers. These are the headline grabbers. NVIDIA just announced a big new frontier model, right? That's very exciting stuff. They're going to open it up for everybody to play around with it, and we'll see where that goes. That's pretty cool news. But this is the GPTs and the Lambdas and all the other big ones built by a relatively small number of companies with huge resource pools, right?
100 million.
And they may do things from training and refinement through inference. They may do it all themselves, right? If I go on that DALL-E thing and generate an image, right? That's pretty much all being handled end to end by one company. Then you have instances where this work is kind of broken up. You have these emerging AI developer communities. Places like Hugging Face that folks can talk to each other, can collaborate, can build things together outside of the constraints of a large kind of hyperscaler company. And in both cases, you've got the arrow going right and the arrow going down from hyperscalers. In both cases, those things may be offered to the market as a foundation model that then an enterprise takes and does their own thing with, right? And so the purple box is, you know, me as the CEO or the head of my IT department. I have a particular business need. I have a particular use case. I'll kind of shop around the different foundation models that are available. I'll find one that fits the bill. I'll then take it, and I won't use it just as is out of the box necessarily. I will fine tune it on some of my own data before I go and deploy it. And then finally, you do have some of those enterprises that are sophisticated enough themselves to be building their own models from scratch. We see that as well, right? And again, that's a small but growing number of companies. So there's a lot of different ways that these things get built, a lot of different people building them and using them. But when we understand this, we can kind of, we also have enterprise grade CSPs as another kind of, spanning the whole slide there as well, and involved in all the different stages from development to consumption. But once we understand this, we can talk about the hardware, and we can talk about, all right, where is this happening? Is this all happening, in a core data center, wholly owned by some hyperscaler and used exclusively for their purposes? Or is it distributed work that's occurring in multiple places? And the answer, as time goes on, is more and more from column B, right? There are more and more opportunities to rent GPU time from service providers to develop things or certainly to fine tune things outside of the core data center at the edge. And so we'll talk about where that's going here in this section. But we see just, for example, an enterprise may take something that was built in a data center, on training servers or racks of servers, and then they may choose to deploy it at the edge, in their own environment. We have a cool example from the London Zoo that's brand new that I'm excited to talk to you about. That's a slide later, but that's an example of kind of how an enterprise is activating, fine tuning, and running inference on a model that they didn't necessarily create from scratch. And then again, when we have the enterprises that are sophisticated and have the resources to do it themselves, often it's a combination of core and edge as well. So in the edge server environment, there's a lot of activity, there's a lot of change going on, and it's self-evident, but I'm going to say it anyway. You can't just apply the same principles that make something a good idea in the core data center at the edge, right? It's a very different set of considerations. And so what we're observing as Solidigm is the rapid growth of this stuff. We have a rapidly expanding ecosystem. There's some data here from EY that virtually every organization is investing in AI in some form or another. There are lots of reasons for that, and many of those reasons drive not only AI adoption, but also drive capacity needs, right? And so, for example, this idea of data security, data privacy, there are use cases, think healthcare environments like hospitals, think manufacturing environments where trade secrets might be involved, where not only can you get faster results if you do something at the edge, but you're also protecting your data. You have much more control over where that data is, and you're able to minimize data transfer, which is not only risky, but expensive. But when you start to push all this stuff to the edge, that's where the black box in the lower right kind of starts to bring in some of the challenges, right? So you're talking about a power budget that's often much, much lower than what's available in a core data center. You're talking about being very space constrained. Some of the servers that we sell into look like the one in the middle. Some of them hang on telephone poles, right? They're sort of purpose built for telecom, and they have very specific and constrained kind of space available in there. So that's where you have to think about whether the form factors of yesteryear, the 2.5 and 3.5 inch drives that have been around forever, are the best approach. And that's why we've seen the proliferation of these EDSFF options, the E3.S, the E1.S, these smaller and more space efficient form factors, where the ratio of bits to the cubic inches that the drive actually occupies is much, much higher in some of these new form factors that are gaining traction. And then also you have serviceability concerns at the edge as well. And so reliability it's always a concern, right? But reliability at the edge where you're talking about a truck roll and I've got to send a technician out to service this thing in a power substation out in the middle of nowhere is a very different prospect than I have a drive that just failed in my data center that's fully staffed and I've got a bunch of spares on hand, right? And so we're quite proud. I didn't come here with a lot of data around drive reliability, but we're quite proud to be, multiples better than a typical hard drive, for example, in terms of annual failure rate. And that kind of stuff starts to matter to customers much, much more at the edge. Here's a couple of customer examples. We'll look at these briefly, and I've got a couple more later on in the presentation as well. But this is one where we're working with Peak AIO, doing some on-prem AI work for healthcare. And so this has to do with, medical imaging, interpreting those images and assisting providers and patients in getting quicker and better diagnoses. This is if you've ever been in a situation where you've waited on results of medical images, it can be a lengthy process, and that tends to be a fairly high stress time in a person's life. And so anything you can do to reduce the intensity of that experience is a pro. And so this is an example where we've worked with PKIO and put our high density QLC SSDs, the 61 terabyte monsters, these are the most dense storage devices on the market today, into their edge servers. And we've seen in deployments with them that they're able to keep the patient data on premises, satisfying HIPAA requirements and other things that are specific to the healthcare world. They're getting faster diagnoses. They're doing it in a much smaller footprint, reduced space, which gives them flexibility to deploy in more places.
So what does that look like when it's deployed on, I presume this is getting deployed at a hospital.
Mm-hmm.
What does that look like from a, is it a 3-server kind of environment for HA? Kind of what's I just see one system there, et cetera.
So just to restate your question, were you asking about the server box?
I was wondering what the deployment looks like, because I guess when I think about edge, I'm always thinking about little things, right?
On device, right? Or
I understand
embedded.
in manufacturing floor, I'm going to put, a visual on every chip that's going across, and I'm going to send that back to a, server on the floor. But then I'm looking at saying, okay, so what does this look like in terms of a deployment? Is this attached then to and you may not know, if it's attached to the devices, the imaging devices, and then I've got a server room that's got like 3 servers in there with 5 GPUs, and we're talking money here.
Right. Yeah, this is an instance where you have an edge server that could be in a IT, co-location within the hospital itself.
Right.
So it's close to all the instruments, all the environment, like an MRI machine, something like that. So imagine like a 2U server, which is packed with tons and tons of data and lots of really intense software that's helping to move that patient data more quickly. So think of it like your typical edge server that is just loaded with really awesome software and lots of storage that will be on location in the hospital itself.
Okay.
So, quick question: would this be a certain type of RAID setup or redundant setup or single device or?
Nope, no RAID setup, single device. All the secret is in the sauce of the software, and I can send you guys a link to the page, which has more and more detail about the Peak AIO solution. They have a few different, types of solutions you can learn from, but it's not a RAID configuration.
Okay.
So how this would be backed up? Like if there's a loss, if the drive goes bad,
Yeah.
what happens? You lose, or there is a backup that is continuously happening in the background?
Oh no, there's definitely backup. I can't go into too much detail because now we're getting a little more, I don't want to speak too much on Peak's behalf, but we can definitely get you more information on what that looks like. But this is a really new and unique solution to the scene, and I think one that we're going to see get a lot of traction in the next year or so,
Well, I mean,
especially in health.
But if you think about what you need here, it's the image itself that's this thing you want to archive. You don't necessarily need to archive the analysis of it if you're just trying to act on it right then. because you can regenerate that analysis of the image once you have the image.
Right.
And the image is already being backed up by multiple vendors. So I think it's really like what's already been mentioned by Andy. It's more on the execution side of things, not on the storing side of things.
Okay.
And I mean, it's a great question. The other thing we can offer up too is if you guys want to speak with anyone from Peak, I can get you connected to just ask some more deeper questions.
So we just say that the functional requirements for the design was obviously access speed, durability, longevity, those type of things.
Yes.
But that, because the other questions we're asking is about just resilience and fault tolerance for that.
Yeah, resilience, being able to access that data very quickly in a kind of non-traditional manner and still have all the goodness of the quality and reliability.
So what do you think future direction of the edge is going to be with this stuff? Because now you have the AI use case, it's going to grow, size-wise, access-wise. Is that
Yeah.
positive vectors for your graph?
It's an interesting question.
And this is where I'll send it back to Ace because I feel like that's a perfect transition. But thank you for the question, Kimberly.
I'm mic'd up. I'm
Oh,
good.
just kidding.
Thanks. So obviously there's a conventional way to address this, which is kind of what we're talking about here. Let's move more compute to the edge. Let's build edge servers and put them in a closet somewhere, right? And that way we're not transporting data over in the network. But if you look further ahead, I mean, there's all sorts of interesting possibilities out there related to compute happening within your storage infrastructure somewhere. There's several folks working on that, right? And it remains to be seen what'll bubble to the top as sort of the most optimized approach there. But certainly this is not where we expect things to remain and to have the same kind of configuration 20 years from now, right? The marketplace full of investment and ideas at this point, and we're watching it with lots of excitement ourselves.
Is there a reason why it's not the NVMe? It just uses SSDs. Does that mean not NVMe?
No. They all use the NVMe protocol.
Okay.
Yeah. We use those terms interchangeably. PCIe, NVMe, SSD. We're talking about the same devices. Yeah.
It's just QLC, more higher density.
Right. Yeah. And we'll get into that in a bit, but in terms of bits per cell, you have options, right? And when we get to our product advocacy at the very end, we'll kind of talk about where does TLC make sense, where does QLC make sense, and why. Good discussion. Thank you. Appreciate the questions. This is the second kind of edge use case that I want to spend just a minute on. And then I'm going to hand it over to Manzoor to start to talk to you about some TCO topics. But this is an example where we were working with a customer called InnoNet. And the goal here was improvement of autonomous driving solutions, right? This is a classic example of machine learning. There's lots and lots of obviously life-changing potential in terms of the applications here, but also lots and lots of technical challenges associated with these. And so this was an engagement where we put 30 terabyte QLC drives into the processors in the car. And because of storage density, we were able to save them some money, collect more data on the road, so higher granularity to the data that they went and then turned around and fed into their models. And we're able to help refine model on larger data sets that stored the longer rides and the higher granularity as well. So these are just a couple of examples, but as I said earlier, there's going to be plenty of activity in the core data center for many years to come. The proportion of that stuff, though, that's happening outside of the core data center in terms of fine-tuning and inference is only going to grow as time goes on. And so storage vendors like us and others involved in data infrastructure really need to be paying attention to that and thinking about how to solve the customer's problems of tomorrow, right? It takes a while to develop these as well.